Okay, hello. I am currently studying for my Calculus B AP exam, and I thought, why not, read through the entire Princeton prep book. I don't know, I'm not sponsored or anything. This one. And see maybe if while I was reading through it, if I could just make some pretty hefty, kind of sizable videos, I guess, through which I can just review all the content so it's all in one place and it's beneficial for anyone involved. So there's going to be there's going to be 3 videos. See, okay, so you're going to have to bear with me. I don't know why the whiteboard does this, but like sometimes I don't know there's something here where it'll just like draw a line until where I'm drawing. But anyway, there's gonna be a Cal 1 video, there's gonna be a Cal 2 video, and Cal 3 video. This is gonna have this one, Cal 1 today is differential calculus. This one's integral calculus. And I don't know what that one. And then this one's gonna have like series and all things parametric. And I promise the writing is gonna be more legible as we go through the video. It's gonna be numbers. I'm not gonna write big words. Anyway, so this is how this is gonna work. And hopefully the little writing bug won't be too annoying. So I'm not gonna insult anyone's intelligence and try and like re-explain the idea of a limit. But I want you to remind you that when we first saw limits, we started getting really ugly graphs, things with jumps and then like asymptotes and then, and then holes. And so, and just in this example, we have 3 types of discontinuities, right? And these are the primary kinds that you're going to be seeing. This one comes from piecewise. Piecewise functions will be giving these kinds of jumps primarily, unless you have this, or a variation of this. This kind of function will give you a thing that looks like, this will give you one of these, right? Okay. It starts at the origin. It does this as 1. This is -1. The whole jump there. That's that idea. That's a very iconic function. You'll see in higher maths. But what I want to point out is, okay, 3 types of discontinuity. This one's piecewise, but these are more common. Okay, you'll see these more commonly. The whole, notice that this one actually does have a limit, right? The limit exists here. But the limit does not exist here because 1, like these do not agree, and then infinite, the limit's going to infinity, and that's not what we want out of a limit statement. So that's what I wanted to really point out. Now there are some things regarding limits that are important, like the rules, like the limit laws. You know what I mean? So 3x squared, limit as x approaches like 2, right? I mean, you can do this 3 ways, and this is a linear operator. Limits are, so you can do, boom, you can pull the 3 out and then solve that way. And then you can say, oh, plug it in, right? So 12. Or you could keep it inside. I mean, sometimes it's better to take it out. You know that if I added like x here, you could distribute the limit to this and this x. If there's division, I don't know, something like this, right? You can pull the limit if there were a limit statement here and I wasn't being lazy. If this were there, you could do something like that and pull it to the top and the bottom. But there is one thing, don't forget, you can take your limit inside. So hold on, what was the problem? That's usually quite good. Arctan. I don't know. But if it's like something like this, you know what I mean? Then you can, pull this entire limit inside here, and you're like, oh my gosh, that's so much easier to know that this is going to negative infinity. So arctan of negative infinity would just be that. Would this be about this value right here, negative pi over 2? So these are some review topics that you've hopefully seen. The big idea I want to cover, though, is limits at infinity and that kind of stuff. So when you see, there are two types of factoring, is what I like to think. Normally you factor something like this, where you're not getting any negative exponents, You want to factor out the greatest common factor, right? It's implied. The greatest common factor gets taken out, but you don't want to overdo it and get any negative exponents. You don't want to factor out a, x cubed, because this would be x to the negative 1 as such. And this is normally so you can do some nice cancellations, right? That's the idea of this. Because maybe there was an x squared down here and you can cancel, and now there is no division by 0. Say if you had limit of x approaches 0, if this were the problem without the cancellation, if this were the problem, normally you'd be getting 0 over 0, right? But you don't want that, so you factor, and then this is basically the same thing you can write when x not equal to 0, and then you can, this graph originally would have produced something with a hole at 0, and then you evaluate, assuming it's continuous, this whole idea, right? Which I guess I can review again. When you see a limit, the first thing you should do is plug in the limit, or think about what the limit value would be. If it's like infinity, you can't really plug in infinity. You think about what it would be at infinity. But in general cases, you plug in this value, and then you say, okay, from there, is this going to give me something indeterminate, right? 0 over 0, infinity over infinity. These are not good things you want to be seeing, because they tell you absolutely nothing. That's the problem with them. Now, 1 over 0 is infinity. This tells you that the graph is having a vertical asymptote of some kind, right? So this is not indeterminate form. This is simply undefined. It is telling you there is the value or whatever is going to infinity. Now, in another case, though, if it is actually 0 over 0, this tells you nothing. It just tells you there's a hole there, but it doesn't tell you like what the value is. What is the limit? What is the limit value? You don't know, right? The hole could be placed at like, the hole could be placed at 0, 8 in the coordinates, or like 0, 1000, or 0, negative 2. Like you don't know. And I'm assuming 0 for the x coordinate of those coordinates, because I'm just going with this idea limit x goes to 0. But anyway, right? Like indeterminate is bad because it's gives you no clues, right? And you'll see in Cal 3, the Cal 3 review, that we have to deal with more types of indeterminates, and there's even more cases of what could be going wrong. So anyway, this is the normal types of factoring that will help you get rid of these indeterminate forms, right? Although this is not always what you want, because sometimes you'll be asked to take a limit as the independent variable goes to infinite, positive, negative infinity, something like this. And this will give you n behavior, right? And when I say n behavior, you should be thinking, oh, asymptote, or horizontal asymptote, primarily, right? That's what you'd be thinking. Okay, so what happens here? You have a different kind of factoring. So the factoring here is you want to be seeing negative exponents. That is the goal. So you have to embrace, and when you see these types of questions, you should be thinking, let me embrace a new type of factoring such that I get as many negative exponents as possible. So here, I'm going to say, okay, I'm going to pull out the 4. negative exponents and terms with a constant in front. Those are with just a constant. Those are very good. And you'll see what I mean. You get 1 plus 3x to the negative 2. And so in both of these things, in here at least, right, in here, you're seeing, okay, there's no positive x. Like the x has no positive exponent. It's actually x to the 0th power, right? So that's good because if this is x to the 0th power, as your variable goes to infinity, this is not exploding so to some infinity value. And when we're thinking about values at infinity, it's really, really difficult to really understand what's happening. So anyway, and this one is a negative exponent. And why do we like negative exponents? Because that'll put the infinity in the denominator, and that will get us to the 0. And it'll zero out that term right there. So anyway, what is this? What is the limit of this question? But, just to ask, right? And actually, this one is infinity because, well, I mean, there's nothing wrong with infinity being your answer. It's just not a limit, but it's not indeterminate, so we don't have to worry about anything, right? Now, what if I spiced it up and I said, okay, oh Lord, x to the 4th in the bottom, right? What if I did this? Well, if you were, this is no longer true. So, but let's think about what would the limit be if we just wanted to plug in first, right? It would technically be like infinity over infinity. Oh, that's so ugly, but I hope you can, I apologize. But this is indeterminate, right? We don't know what infinity over infinity means because infinities can be greater than other infinities, and you're like, oh, is this settling at a constant value? We don't know, right? So, and I'm not technically plugging in infinity. This is another thing I want to say because in Cal 3, you'll see this again. I think of like turning up a knob. I'm like thinking of the numerator, like turning up the knob of the numerator, and like it's rising up to infinity as the independent variable grows, and I'm turning up a knob for the denominator, and that one's growing as well. So it's infinity over infinity. Now, where do we go from here? Okay, this, I don't get it. I really don't get it. Maybe that was the problem. Hopefully. Okay, let me erase this. Okay. So if this is the problem, still same problem, right? How about we try and cancel in a way that gets rid of the independent variables that are just growing crazily to infinity, right? The only way you can do that is, either get rid of the x entirely, get x to the 0th power, right? That's how you get rid of it entirely. So it's not going to grow because it can't. It's no longer there, right? Or we can get x in a negative exponent because we can't hope that this one's going to cancel perfectly because you can see why. And so x to the negative 2, well, this one will just be 1 over x squared. And then when the limit of, x going to infinity of this, well, this one's just going to go to 0, right? So that's the idea behind this. And so and this is when you brought back that entire idea of, okay, let me factor differently, right? Let me factor in a weird way, right, to get as many negative exponents as I can. And then you cancel this out. Don't drop the limit statement because that will always cost you points. And then you'll have limit as x approaches infinity of 1 plus 3x to the negative 2. And well, you know that this is the same thing as 3 over x squared. As the x squared grows crazily, the 3 will stay constant. It'll get overwhelmed. It'll just be a very small value, and it'll actually approach 0 because it's a limit. And so actually the answer is 1, right? But if we saw this in pre-calculus, we wouldn't even hesitate to just use our understanding that, okay, what is the end behavior here? There's going to be an asymptote at 1, right? What this tells us with the limit statement is maybe the right word asymptote. The asymptote on the right side of the graph is 1. That's all we could really gain from this. From this piece of limit statement. But, here we think, okay, we think in terms of the greatest term in the numerator and the denominator, because that will always overshadow the rest, right? However you move the independent variable, get crazy big, get crazy small, the largest term, the greatest degree term in the numerator and denominator, these will always be growing the fastest. And that will always overshadow the rest of these terms over here. And so we think, okay, if n is the numerator one and m is the denominator's greatest term, if n is equal to m, you take the ratio of this. And so in this case, it's 1 over 1 because the coefficients are here. So the asymptote's at 1. If n is greater than m, well, then the numerator is growing way faster than the denominator is. It's going to grow crazy. The denominator won't be able to divide out enough value from the entire function. So it's just going to go up to infinity. The numerator is getting bigger than the denominator is. And then if m is greater than n, well, it's going to actually go to 0, because if it's like a race to infinity, this one will always like pull it down. It's kind of like, we call it bottom heavy in Cal 3 a lot, bottom heavy functions. And so this is kind of a general rule to have. I want to remind of these identities. Limit of this as x goes to 0 is actually 1, I believe, right? Yes, this is 1. And x, remember that the x, at least, this is a kx. The x is in radians. In radians, not equal to radians, because that would make no sense. Okay, this is an important thing. And if you see something like the limit of maybe the limit of 3x over 3x, well, this is still 1. Another thing that you can probably derive after doing a certain number of problems is, okay, what about the limit as x approaches 0 of this? Well, this one you'll actually find is 3 over 2. We just take the ratio of these. The cosine type 1 is then kind of the same thing with the limit as far as that goes. It's still going to 0, but it's cosine of x minus 1 over x, and I think you can just do the k here and k here. But besides the point, not sure how much this will come up on the exam. This one is just 0. And when I urge you to see that we like cosine of x in the denominator, okay? This is always fine. We are completely okay with this because the limit of x as x approaches 0 of something, of cosine of x in the denominator, well, this is not going to be 0, it's going to be 1. So it'll just be 1 over 1. So when you do these kinds of algebraic manipulations with these trig identities, cosine of x in the bottom is always fun, but the x in the denominator is not fun. All right, and so that's how that works. Continuity is something I just discussed, right? But the formal definition, remember, is x approaches c from the left of f of x. F of x is the same thing as limit as x approaches c from the right of f of x, which is all the same thing as if you just simply plugged in a c for this f of x, right? That is what this is all equal to. And I hope this was ringing a bell, right? Boom. This is the c you're interested in. This is actually not an open circle, it's closed, right? The right, from the left you approach it, from the right you approach it, boom. All right. Piecewise, if you see it in piecewise form, just try and verify these 3 facts. And if you're coming from the left, right, you'd use the piecewise part of the function that is less than the c. And if you're on the right, if you're trying to verify that idea, you're just trying to make sure that it equals this f of c value for that function where x is greater than c. I mean, I can make more sense with like an example. X is less than 2. X is greater than or equal to 2 if 2x plus 1. Right? In this case, okay, what is f of, well, we know that the c in question is 2, right? This is the important number that we're going to be, looking at the transition across. The continuity of this is unsure for us. So we look, okay, what is f of 2? Well, 2 is going to be using this function right here, 2x plus 1. This is 5 because, x is equal to 2 gives us this as well. The limit, and then you just say, okay, what about the left-hand side? What is the limit as x approaches 2 from the left of f of x? Well, from the left, it's less than, and so it'll be approaching x plus 1, evaluated. This bar means evaluated. X equals 2. Well, this equals 3. So already you can start to say it's not, it's no good because the value of the function is not equal to the left limit. But then you can say, okay, what about the right limit? And it's greater than 2 for this function right here. So 2x plus 1 at x equals 2 is just 5. Right? And so just to the right of it, it actually does make sense. And so maybe it'll look something like this. This is what it's getting at. And so it does, obviously it doesn't look like that, but no matter what happened to the left of this point, right? There's an open circle here. It jumps up to this value, not continuous. Okay, so that's kind of the piecewise idea. You want to just check all 3 statements and use the correct function depending on what you are at c, greater than c, less than c. Okay. Types of discontinuities. Yeah, we already know this. Remember that if you do look at a limit, right, and you can actually end up canceling out a factor in the numerator and the denominator, right? If it's something like this, right, where it was 0 over 0 initially, if it was 0 over 0 initially and you did something and you factored out to get it something like this, and you say, okay, this cancels out, this is actually a whole, 3x squared plus x over x. This was the original function that I just undid for this step, right? This is where this came from. This would be a function that looks like this with a whole at 0, right? And so this little 0 over 0 place where it goes 0 over 0, and you can divide it out perfectly. Remember, this is a whole. And if you now solve the limit statement without the discontinuity, right? This is a continuous line, right? This will tell you, and this is a special case, and this is why I really enjoy wholes, like the continuity problem with wholes, because it's like you're no longer, if you can just take out the whole, you can just assume this is like a continuous line, and then you say, okay, what would it have been without the whole there? It would have been equal to 1. Sorry, I can't do math. Cannot do math. Okay, the limit of this would be 1, right? If you plug in the 0, and that's actually the coordinate, the y coordinate of this whole. And the x coordinate would just be where what x value would make it undefined in the first place. Sorry, not undefined, indeterminate in the first place, right? So this is the whole idea, and it's a very important thing to note about the wholes in particular, right? Just assume it's continuous. What would it do if it were continuous? Because you know that the limit of a whole exists. That's why you can't assume it's continuous, because if the limit of the whole exists, and you just think the whole itself is just plucked out, but it should be in there. You just fill in the hole and you think about it, and it'll tell you actually what the limit is. And it's kind of a cool idea. Okay. The definition of derivative. So we think, okay, Okay. What was that crazy arcane limit definition of a derivative? It was literally, this is one of them, right? This was one of them. So it's h is going to 0. Well, I mean, we can rederive it actually if we think about it. Right? So you're at some x, and well, you're at some point that's not exactly x, right? And so it's this whole secant line idea, right? And so you're over here. Let me make sure that's right. Yep. Okay. So you have this curve, right? And honestly, you don't need. Okay, like this. This is the curve, right? And this is the x you're at, right? And you're thinking, remember why this works, so you can rederive it and don't have to memorize it. A secant line would normally just be y, the slope of the secant line at least, right? Would be like this, you know? This would give you the slope of it. And then you're thinking, okay, this is essentially a secant line. This is x plus h. And as h gets closer and closer, it's no longer this secant line. It's actually this line that over time starts to get closer and closer to this value at tangent. And so eventually it is going through a single point. And after your limit of h goes to 0, you're actually just considering this point, just this point, and the slope of it, right? But, you know, if you try and think about it any other time, you're thinking, oh my gosh, why doesn't this work? You know, there'd be 0 division, right? So you're going to have to do some cancellation. And that is normally where you get introduced to this kind of limit algebraic based idea of how to do power rule, right? I'm not going to do all that because you'll know power rule and hopefully you'll be able to apply it. And remember that sometimes they might ask you, not in this definition of the derivative, but they might ask you like x approaches a of like, I forget this part right here. But there is a different definition, right? And if it looks kind of like this idea of like x minus a on the bottom, this actually might be simpler. But it'll give you the function value here. I don't really remember. Forgive me. I really don't remember. But there is another definition. And then sometimes you'll be asked very simply, what is this limit value? And instead of having to do all the algebra, what did you have to do? All you had to do was figure out what the function itself was, because there was like an f of x term here. And you're like, oh, yeah, that was the function itself. And then you just, then you already know what the function is, and you know what the point is. The x value itself is just a. So then you maybe f of x, you can just look at this limit definition and figure out that it's like x squared, and you know that a is like 2. Well, then you know f prime of x at 2, because maybe this idea, f prime of x at 2, is 4. I mean, it's very simple from there. And why do you know you're doing the derivative at 2? Well, this is this unfinished definition is the limit definition of a derivative at x equals a, and our a is 2. So that's how that idea all comes back. I'm not sure if that'll be covered. Hopefully not. Differentiability. 3 things you don't want are cusps, because like, what is the tangent line in this case? You know what I mean? Like, what is the tangent line? You don't know. You really don't know. Then there's also vertical asymptotes. Yeah, these are not differentiable because like it's discontinuous there. And yeah, I mean, discontinuities in general, they're pretty hard to take a derivative of. Like what is the tangent line here? Like, you know, Um, so discontinuities, and there's also vertical tangents. So vertical tangents are like something like this. Oh, awesome example is x to the 1/2 power. And there's always a discussion of like, I mean, does the limit even exist? Because it's like an end-to-end point, and that's a whole debate in math, I believe. But like the limit is x approaches 0 from the right, or just 0 in general, right? Because you can't approach from the left, and that's the debate, sorry. And so, this here, it goes literally at some point, at x equals 0, the tangent line is actually vertically facing. This is meaning that like, if there's like modeling some particles in motion, it's going at an infinite velocity. And that just simply does not make sense. Anyway, okay, differentiability, that's done. We're making good headway. Basic differentiation, power rule, not going to review this. Just drop the exponent down in front and reduce the power. Right? But be comfortable with like, okay, of course you should be comfortable with like, if you see the powers 1/2, 1/3, 3/2, negative 1/2, these kinds of things, you should be able to easily subtract 1 from that when you're reducing the power for like the second step of the power rule, right? Addition. This is when I think of derivatives, though. I always try at least pay attention to where any plus minus signs are, because that normally saves me from forgetting to do something like chain rule, or product rule in particular. It's because if it's like this, well, I know that this can actually just be like written like this. There can actually just be another derivative part right here for this statement, but you can't separate this function of x, which is just a simple line, from this function of x, and that's why the product rule comes into place. What is the product rule? Derivative of the I do derivative of the first because it stays intact with the should I do g of x? Okay. It kind of looks like the quotient rule, which I guess we can look at next. Yeah. The quotient rule would just then be actually this is f of x, g of x, right? The order really doesn't matter here because addition, but as soon as you start to look at the subtraction of this, right? Derivative of the first, this is why I like to do the derivative of the first anyway. I just sounded like a robot. Derivative of the first times the derivative of the top times the bottom minus derivative of the bottom times the first top. God, that was embarrassing. Okay. I don't know why my throat sounds like that. Then just square the bottom when you divide, and this is a minus sign. Just reminding you of formulas there. Let's see. What else do they want you to know? Chain rule, of course, right? I know everybody knows this. When it's like 6 days before the CalBC exam, but just for completeness, something like this, and you can stack this idea forever and ever for as many inner functions as you want. And I know the MSMS teachers have a tendency at least to give you these hairy, very intense chain rule problems, but it'll give you good practice, right? Oh, and I also recommend if you see some chain rule problem that looks like this, you know what I mean? I mean, of course, there might be some more. This is kind of misleading because this is truly, because it's kind of compacted. This is what this means, right? So then you would chain rule by doing this one first, and then you would do this, and then you would do this, okay? So that's, of course, very important to look at. Trig functions, derivative of sine is positive cosine. Derivative of cosine is negative sine. I think I don't know, this idea has kind of helped me through a lot. Cosine is this generally positive thing. In my mind, it's this like happy, yay, cosine. Anyway, so derivative of the cosine will land you into a positive happy cosine. But if you're taking the derivative of the cosine, I think I've done this for every single derivative integral that's involved tan cosine. I thought, okay, derivative the cosine, you're not turning into this cosine anymore, you're turning into a sine, which will give you a negative sine of x. But the sine is always happy to become a cosine because it's such a happy little thing. So it's positive and this one's negative. And we can look at the integrals later in the next video. But tangent. Derivative of tangent, I want to remind, is secant squared x. Okay, cool. Yeah. Don't want to hammer in that idea. That's kind of boring. Also, secant x, derivative of this. I remember, how do I remember this? I kind of just remember that tan becomes secant squared. And then I have to know that, okay, if you're taking derivative of secant, it can't just be itself. Like derivative of secant's not secant squared. That wouldn't make any sense. Derivative of tan, okay, secant squared, that conversion makes sense. So then I think, okay, then it has to be the other one where it's secant x times its partner, just tan x in this case. And dy dx of, actually, they didn't actually go over the, that makes me sad. Hold on, I'll go over it. Yeah, they didn't add that formula. Derivative of cosecant of x is negative cotan x cosecant x. And so it's again the same kind of argument. Why would it be cosecant going to negative cosecant squared? That doesn't make sense. It's just itself. But the thing that could go to negative cosecant squared of x, the thing that could do that is a derivative of cotangent, right? So the tangent and the cotangent get these squared types of derivatives, and that are based off of these secant cosecant values, and this derivative of the secant values will just be this kind of expansion type thing. So that's just make a whatever remembering tool that you need, mnemonic or whatever you need, I guess. Graphing derivatives, just be very good about identifying where, like, if this is, sorry, if like this is the derivative graph, you know what I mean? Right, like you're gonna probably have, you're going to have relative maxima minima, because something we'll cover later is you're passing through a zero. If this is the derivatives graph, this is so ugly. Okay, you know that at this x value, this x value, this x value, you know what to look out for, that kind of stuff. You also know that maybe here there's a second derivative change. And so, this is something we'll see later in this video, but the f of x function, where to look for the relative minima, concavity changes, those kinds of things. And always remember that that since it's a derivative graph, any constant, any vertical shift that you apply is suddenly removed from the function. So, if it's asking you for a potential, to like choose a potential f of x graph, it could be any one of those things translated a million units upward or downward, right? So you have to, just as long as the slopes and the shape of the curve is the same, it'll be okay. That's the right answer. Okay. Implicit differentiation. This idea comes in handy because sometimes you aren't working with functions that are just y of, these aren't just functions where y equals f of x. Sometimes they're not functions, they're relations. And sometimes, I'm not going to differentiate between those two statements, but and to elaborate, maybe you might something like this, you know? Like this does not look like something where you want to solve for y in terms of x and then take the derivative of it, right? Like that's not going to be fun. So then but if you do still want some notion of this idea, dy dx, which is what we've actually been doing all this time, you know, y equals x squared, well, dy dx is 2x, right? All you're doing, you're applying this linear operator to both sides, right? And so what the idea you want to preserve is that, okay, we can't get in this nice form. We still want this kind of notion of dy dx right here, right? But why can't we do it with this itself, right? So what this is saying is, you know, there's some, it's like compacted almost, like the relation between y's and x and y, maybe it's better to say, the relation between those two variables, changing the x will change the y, of course, right? That's what dy dx is saying. Well, maybe there is some intrinsic, like, bundled up relation in this y squared plus y thing. And so if we want to isolate that and get rid of that and put it all on the right-hand side, so we can say dy dx equals something concrete, well, that's the goal, and I mean, we'll do it if we have to do it. And you'll see what I mean. Well, this is where implicit differentiation comes into play, where you take the derivative with respect to, this is the part that's important. Well, since you want dy over dx, you want the dx on the bottom, well, then you do this. And you apply that to this right-hand side. Right. And so you'll get 2y. You'll differentiate y squared in the very same way. And I don't want to teach this again because you've gone through Cal 1, if hopefully, or maybe if you're watching this video just to get a head start. There's kind of like a chain rule where y squared is being differentiated with like respect to the y, right? The change in dy with respect to the y, and then you're multiplying it by this dy over dx idea. So it's like d over dy of y squared. And then you're understanding, okay, once we know how the y's change, let's relate it back to this x, and so that's what this multiplication thing here is, and that's what we see, right? This 2y times dy dx idea. Okay. There's so much more to it that I would want to say, but we don't have time. So, and then the y with respect to x is just dy over dx. And it's actually something we always did, right? And then you come over here, and this is the same old business that you've always done. What was that? I couldn't read my handwriting for a second. Okay. And here we don't see a dy dx. Well, obviously, because there's no y, and that's the perfect point, right? And it's such a like simple idea. Like there's, you don't see dy over dx over here because there's no y's on this side to differentiate. It's also this idea that behind both of these, I'm going to write it over here, though, because this looks like a partial derivative. I'm sorry, or well, a really ugly one. This is actually technically, maybe it's back there, but what is the change of the x with respect to the x? Well, it's just 1, so there's no need to write it back there. And that's just another way to see that maybe you're not entirely doing a different idea. You're saying, how is 3x to the 5th changing with respect to x? But this is the rate. And then you're saying, okay, well then how's the variable changing with respect to x? How's the variable changing with respect to x? Well, it's, dx over dx, that's the same thing. So it's just 1, right? So, and then you would just factor out the dy over dx. Okay. And so you just get 2y plus 1 on the left-hand side equal to this whole shenanigan. Divide by the 2y plus 1. right? And that would give you your derivative in terms of x, but also in terms of y. And this is the idea I was trying to tell you, that your change in dy over dx for this problem has some packaged in rate. That's also, any change in the x is also changing the y in a little bit, and then you like add the y's together and all that kind of stuff is kind of like making your change in y more than you maybe think it is. And so that's why you're now in the end kind of like dividing by this dy and getting rid of that overdoing, or it's just simply how much does the y change with respect to the x. Okay. Second derivatives. So in that case right there, you ended with something with just x's and y's. Second derivatives are simply, you do the exact same thing. You apply the d over dx operator to not only dy over dx on the left-hand side. Okay, I'll rewrite that. I'm not going to be lazy. Okay, and then you apply your d over dx to whatever that weird derivative thing was, like this, I think that's what it is. And so then you got obviously d squared y dx squared. But when you do this whole idea, you're gonna have to do quotient rule. And when you do quotient rule, this y is going to produce another dy over dx. But you don't want your second derivative to be with respect to your first derivative. You just want to know, if I change my x and my y in some way, what will be my second derivative value, right? And so this is why when you see your dy dx pop up again, you know, since you're calculating the second derivative using the first derivative, this is the first derivative, by the way, you can just plug this back in at the end. And so you're going to have a very massive, maybe simplifications will help you out, but you'll have some derivative with respect to, x and y's, and there will be a dy dx, and then you'll replace the dy with dx with, well, what it was that you calculated in the last slide. And I'm going to clear it all because I'm done. Okay, so applications of the derivative, right? Equations of tangent lines, normal lines, that kind of stuff. This is such an important formula. I can't stress it enough. We always grew up, I always used this formula when I was in like middle school. And in the end, you do convert back, because it's very simple to look at this, and oftentimes you do write in this form. Oh, don't clear it. But this is where you start, right? Because this will give you a very good idea of what you're doing. You say, okay, there are three things that I don't know. There are 3 degrees of freedom. There's the slope, there's the x1 and the y1, okay? And these are simply variables that produce a line. That's what this is. Variables that produce a line. But how do you know if your line is this one, this one, this one, this one, this one? How do you know which line it is? Well, you fill out the degrees of freedom, the slope, and the point through which it passes, and you realize, okay, this is very easy. So you first then, why is that big? Why did I make such a big deal out of that? Okay, you first find the slope. And how do you find a slope at a point? You're given x equals like 3. So actually this kind of fills that point out, right? You want a slope, you take the derivative and you evaluate it. Use this bar notation again. Evaluate it at x equals 3. And then you get the slope value that produces it. And then you say, okay, we know what x we're at. What about the y? So then you take the function itself and then you plug in the 3 and then you get some y1 value. And then you just construct this and you're done. Very easy. Very easy. Normal lines. Normal lines are another fancy thing to say perpendicular, right? And we learned the slope. If this is a slope of this line, the perpendicular line will have a slope of negative reciprocal. So flip the fraction and add a negative sign in front of it, right? And that'll give you the slope of the perpendicular line. And another way to formally kind of like say it is slope of I don't know, regular line, the original line that you had, right? Maybe this one, times slope of the perpendicular line equals -1. And then this kind of, you can show it for yourself, but this is the same thing. And you still, what are you doing? You find the slope of that point. Both of them are passing through this same x1, y1 point in the plane, right? Same thing, it'll be going through here and here. So then you found the perpendicular slope and you found the other 2 degrees of freedom, and you construct your same equation, and you can, there you go, equation of a line. All right. Okay. Mean value theorem. I don't know why this book doesn't go over IVT. So I'm going to go to intermediate value theorem first. Right? This idea was that as long it has nothing to do with derivatives, thank God, right? Less to worry about. So if you have anything, you construct any value. Actually, I'm going to redraw this because it's not going to teach the point that I want to teach. Oops. I'm just going crazy. It is actually midnight for me right now. So when you see this, right, it doesn't have anything to do with the derivative. All you have to know is that if this is A, this is B, that it has to be continuous from A to B. If it's not continuous, you can break it. Literally, you can break it. And you can say, okay, maybe this is where the value is. You know, and then maybe this says literally nothing about your graph. Like if you have a discontinuity at A and at B, you know, then you can do crazy things, primarily jumps, and those will kind of throw off the intuition you get. But if you know that these are indeed defined points, A and B, at A and B, x equals A and B, right? And the function on the graph is actually f of A, and this is the point on the graph is f of B. You know, here, if we look at it this way, well, what does IVT tell us? Well, we know that if one of these points is above the x-axis and it's positive, and one of these points is below the x-axis and negative, well, it'll have to have crossed somehow. And it crossed over here for us, quite close to the B, but maybe it could have done something like this, right? Maybe it could have crossed several times, but that's not the point, right? The point is we have to just know that it crossed one time, which it did, because at least one time, right? So, and when you do free responses, you should be restating kind of like the conditions that you need to meet. Since f of x is continuous from A to B, and since f of A is positive, and since f of B is negative, it must exist some point f of C, you know, where like C is less than B, is less than A, or something like this, such that f of C is equal to 0 or something, you know, that kind of fancy way of saying it. But you always have to say the condition for free response, because, or what else, you know, you might lose some points, and you don't want to lose points. Okay, mean value theorem, this starts to do calculus. So your condition's still continuous at A and B, because it's kind of like a primary thing, because math knows that if it's not continuous at A and at B, you could do some crazy things and break it. But it just has to be differentiable in between, not at those points. And you know why. I mean, it's kind of intuitive why. But if you have some point here, it makes sense. Their secant line, the slope of the secant line, so f of B minus f of A over B minus A produces a slope such that some f of C, some f prime of C is going to have this slope. Right, so some point on this function is going to have a derivative that's parallel. Sorry, well, that's going to have a derivative that has the same slope. It has a tangent line that is parallel. Same idea. This was not a very good visual because my secant line kind of sucks, I think. So maybe this is where it comes parallel. That right there. But that's a secant line. Just the same idea. Just pretend I'm good at drawing, right? Okay. And Rolle's theorem. Rolle's theorem just rolls right off of this one. Actually, Rolle's came first, I believe. But Rolle's is saying that if it's kind of like furthering this idea, it's like a special case almost. I think mean value theorem is a generalization of Rolle's, right? That if f of b minus f of a, b minus a is actually 0, and if you know something's 0, you have, and it's like this, the numerators, which you're setting equal to 0 to get it, because if denominator equals 0, it's undefined. So I mean, this is another idea that comes up constantly in calculus. Numerator is equal to 0 if the whole thing is 0. Anyway, so if this is 0, well, you know that some point on this curve is going to have a 0 slope in between b and a, right? And this does happen. But why do you know this? And what does this mean? To have this happen, f of b has to equal f of a, because f of b minus f of a equals 0 if f of b, this is the idea I was getting at a second ago, if you're setting equal to 0, they equal. And why does this make sense? And I'm going to kind of get a little theoretical here now, but only because I feel so passionate about this. If you're trying, okay, so when you have a theorem like this, it's saying it happens at least once, even the most simple case will be satisfying it, So if you have a function and this is the end point, this is the start point, this is the end point, this is x equals a, and this is x equals b, well, even the most simple case of just a straight line, it'll connect them and you'll have a slope that is literally the secant line, right? In the most simple case, it'll happen. And of course, that means in more complex cases, you'll see this happen as well, right? Now, Rolle's is just saying Rolle's is simply saying that if this line, but now this point, we're actually on the same, and I don't want to give you this false idea that it has to be on the x-axis and the y equals 0. So if you see something like this, even in the most simple case, there is a secant line that connects them, and the slope of this secant line is a 0, right? Meaning that at some point, no matter how you construct it, it'll have to turn 0. And then going back to the converse, now that you've seen this, the Rolle side of it, even here, like just right above it, even if it's right above it, right, you have no way of saying that it'll turn around. It could just do something like this, right, and just connect. You have no way of saying that it's going to be flat at some point, although that looked kind of flat, but the intention was that it's not flat. But as soon as it is on the same kind of the same y value, right? As soon as they're on the same y value, you know that they have to have, it has to come back at some point, because at the very least, it'll be going across, right? And I think that's just the fundamental idea, and that's just so cool why Rolle's theorem works. And that's it also, and the conditions for Rolle's theorem are the same for mean value theorem, so don't forget to state those conditions before you apply it. And yes, okay. Maxima, minima, okay. I also feel kind of passionately about this. You really have to understand that just how to go back and forth these lenses. So when you're given a problem, and this is going to come up a lot, maximum minimum problems, in my experience, you think, okay, I know the first derivative value. What does this say about the second derivative? What does this say about the zeroth derivative, which is how I'm going to, my notation for 0th derivative is just simply going to be f of x. That's what I'm going to be referring to it as. So there are different levels of viewing these things. Levels of organization is kind of the science, the idea of it. So this is the idea, right? How do we start here and go here? Well, if you see a root, if this is equal to 0 or undefined, no matter how you construct it, given these conditions that these are, continuous between these intervals or whatever, just for the sake of simplicity, right? If it's 0 undefined, you know that something here has a possibility of having maxima and minima, right? So if this is the f prime of x graph, you know that here there is a maxima minima, here there is a maxima and minima. Why do we know this? We know this because the sign changes, and that means in f of x, it was rising, it was positive, it was rising, it was rising, and then it hits a 0 point, and then it's negative, and so now it's negative, and it's going downward, right? So since it's negative, negative slope, okay? So this is why we know now if we see the f prime of x graph like this, we know that the f of x graph has to look something like this. And the same idea happens here, where it's like, actually it's a minima here actually, because it's going down and then suddenly it starts picking up in positive slope. Although, again, this idea has to come back for you when you're saying, okay, what about if f prime of x is this? What if f prime of x is a saddle, or no, sorry, if f prime of x bounces, right? Multiplicity of 2, this kind of idea, right? Well, you know then that you can't really conclude that there is a maxima or minima here because, and actually this idea comes up. Multiplicity of 2, this is x squared, right? Its root at 0 actually happens twice, multiplicity of 2. This is f prime of x. But what about f of x? Well, if this is, if I integrate this, I know this is, or if I just kind of work backwards with logic, that this was originally the x to the third graph, and tell me where the minima or maxima is here. There is not one, right? There's no relative one, at least, right? And that's the idea. This is a saddle point because that's change. There's no change in sign. So for there to be a relative minima or relative maxima, there has to be a change in sign, okay? And then we think, okay, but what if the first derivative graph has, I like working from the first derivative perspective because you get to look forwards and backwards, kind of. So if the first derivative graph is, has a mound, what if it has a mound right here? We know here that is actually a relative maxima. And since we can say that, we know that there must be a root in the second derivative graph. So this is f prime. So we know that the root on the lower dimension, kind of that's like how I view it, like lower, higher. So if there's a maxima on this dimension, there must be a root on a lower dimension that kind of builds it up. I don't know. You do get what I'm saying? Like there's a root under it, and it's a root of all things stems from it, and now something's grown out of it. And it's a mound. There's a minima, maxima. There's a hill coming out of it, maybe if it's a minima. But anyway, this is just how I remember things. But since we say that the f prime of x graph has a maxima, the f double prime of x has this kind of root here that actually goes from positive to negative here, right? And if in a free response question, how to justify that these kinds of things, the sign change in particular, you need to say it. You say, if you're on this interval from like A to B, right? Open, close, whatever. You need to say, you know, right before the x, it changes, it was positive, but like right after, and you like, you know, plug maybe some points in, or, you know, make a point that the sign changes on the second derivative graph, and that's why there's a relative maxima. You know, it go change from positive to negative on the second derivative graph, so there's a relative maxima on the first derivative graph. So you need to clearly state that where this is happening on the interval of a to b, right? Changing at an x value, maybe c, right? All these things to be stated. Don't forget all those very important pieces of the puzzle. You need to tell them on the test. But what does this also say? This also tells us that there's a concavity change on f of x, right? This second derivative change is telling us this is actually an inflection point. And it's actually going from something concave, what is it? Up to concave down. Yeah. So maybe it was like this. And so now it's like this. You know what I mean? And I think positive facing up, concave up, negative facing down, concave down. Okay, these kinds of ideas. Second derivative test comes in handy. You think, okay, I don't want to check the sign change. I want to just check first and second derivative. I don't know when taking the second derivative is easier, but sometimes it can be with the trig, right? You say, okay, you know, I find 0 point in the undefined point, and then I plug it into the second derivative. I realize, okay, undefined is more of a niche case, but don't forget that things can be like undefined, be a relative min, right? But you say, okay, what's the second derivative saying? There is a 0, and if there's a 0 and we say that there's a positive sign on the second derivative and the negative sign at that same c value, if both of those conditions are met, f prime of c equals 0. Can't really remember for the life of me if it's undefined too, but I'm not sure if that matters right now, because like concave up cusp, you know. So I'm kind of hesitant to say anything false. But if it's like positive or negative, well, then you know it has to be a maxima or a minima, depending on what sign you get, because the only times you'll get like a saddle point is maybe if it's like a concavity, if it's an inflection point, you know what I mean? Or something like that. Like you won't be getting a 0 if it's a max or a min. You'll definitely be getting something like this, where like, okay, this is clearly in the middle of a concave down section, or okay, this is clearly in the middle of a concave up region, right? And that's why there's a 0 here. And since there is some clear concavity, this is the concavity sign, some clear concavity, well, now we know there's a relative min or a max. Now, if it were 0, we would have no idea, right? Like it would probably be a saddle point in that case, where this one was concave down, this one's concave up, concave down, concave up, concave down. So these are the cases. So for a second derivative test comes in handy just to make sure you get the signs on the second and the 0 on the first. Okay. And EVT. EVT comes up a lot. Extreme value theorem. What is it saying? Oh, let's look. It's saying that if you have a closed interval, there exists some extreme maxima or minima, right? So why? Because and if it's continuous, and we can look it up actually. Well, let's look up two things. Let's look up. Let me share the screen. Well, actually, let's not share the screen. I can look it up on my own. We look up conditions EVT. We see that if it's a function on a closed interval and continuous on a closed interval from A to B, then yeah, okay, cool. And also, we know, let's look at second derivative test, just to make sure. Yeah, it is 0. I think the f prime of x should be equal to 0. Yeah. Okay, cool. So what I've been saying is correct, is my point. Okay, good. Hopefully, well, mostly correct as far as what I've checked so far. So you need the function that you're drawing to be continuous from A to B. Continuous, right? And then you can confirm that there exists both an extreme max and extreme min. Okay, this is the idea. It's continuous. Again, these conditions are very important to remember for the test, right? Not because there's a closed, because it's closed. You know, if all goes to heck, right? And it's just continuously growing, well, this is going to be the max, this is going to be the minimum. And it comes back to this idea of what is the bare minimum that a function can do. And then the more complex things, I guess, will still have these intrinsic characteristics. So the max exists, there exists some max and exists some min, right? But it doesn't have to be the endpoints. The only other way it could be, so the only other thing, that could be a mapped extreme max or an extreme min are critical points or the relative mins or the relative max. They could actually be extreme, right? So in this case, this is the extreme value. And in the questions, they might ask at what x this extreme value occurs, extreme max. Maybe you'll have to say x, but if it's saying what is the extreme value or extreme max, you know, absolute max or absolute min, like all these ideas, if it's saying that, then you'll go to the y values. Or maybe the coordinates will be asked, so be sure to be wary of that too. I just keep giving random advice throughout. Okay, so this is the absolute max. And so the only places that you could see an absolute max occur are at a relative max. And how could a relative max come about? Well, this goes back to the first derivative, second derivative tests ideas. You need the f prime of x to be 0 or undefined, and then you need to check if the sign changes from positive to negative for this case. But you know what could also happen? It could be a relative min. Oh, that's not a good thing to look at. Okay, this could happen. And so this case, this is the relative min. And so same kind of check, but you need to check that it goes from negative to positive on the f prime of x graph, right? Those values need to be negative over here to the right of it, to the left of it, and it has to be positive to the right of it, that kind of idea. And I hope all these things are reminding you of all the things that you need to remember. And then, you know, why does this not work for open circles? Because there's no guarantee. Sure, these are relative and actually thus in this just in this drawing extreme, there are extreme and absolute max and minimum here in these drawings. Although if in the simplest case, right, you have something like this, well, if it's an open circle, you can approach this open circle for as long as you want, and you'll never know, you know, if this is -1, is the absolute max, is it at -1.00001 or is that -1.0000001, and just keep approaching this forever, and you're never sure what x value has this absolute max. And so, but you can have relative mins and relative maxes, and thus absolute maxes and mins if they're crazy enough, but it's not guaranteed. This EVT, if it's closed, right? If it's continuous and closed, it is guaranteed. And that's what I think, another thing, it has to be closed, which is something I keep saying, but in the conditions, remember that it has to be closed. Okay. Okay, optimization occurs. This is a topic that comes up just to know optimization modeled by something very simple, usually like an area or a volume type of problem. And you're just changing one of these aspects. You shouldn't be working with two variables because that would not be a calculus 1 problem. But if you're working, so if you get two types of variables like length and width, you want to standardize them to one variable. Maybe the length is 2 times the width, right? So you'll have 2 width times the width, right? Maybe this will be some way you rewrite it, but you want a single variable. You want to work with it, and then you want to then say, okay, you want to produce some sort of graph that is saying, okay, this is the area graph with respect to x. And so maybe it'll be doing something like this. So there is some place, some x value where the construction that creates, the area is at an absolute max here, right? And that then becomes your kind of like an EVT process where you're trying to optimize in a real world application for why you're actually finding this absolute max. Like, why would you care about an absolute max? Well, this is an optimization problem. You're saying, oh, okay, if you're modeling the area, well, very clearly at this specific x, you're producing a very large area, and this is the optimal thing. Or maybe it'll be actually asking for minimize the area, right? Maybe it costs too much and you want to minimize the area. Maybe the same idea will occur, right? And how you do this, of course, you take the derivatives. Why? Because, well, that will give you where the 0 occurs. You're doing this whole EVT process again. You're trying to figure out, okay, where is it 0 or undefined? And then you're trying to figure out if the endpoints itself are going to be the max in the end. It doesn't actually matter. And that kind of stuff. Okay. And make sure you check the sign changes because that's important for optimization. Okay. Gosh, Problem 1 was quite dense, to say the least. Okay. I'm not going to go over curve sketching because it's been kind of this entire video. It's already getting quite long. Related rates. Okay. You want to, they're very typical problems that come up in related rates. All you're doing is you're kind of using a formula that you've learned already, kind of, and you're taking this formula and you're differentiating it. You're using implicit differentiation, actually. And so if it's like an area problem, oh, it's, what is the rate of something? Let me, the area with while, what rate is the radius expanding when the radius is 4? And you know what the area is growing at a rate of, like that kind of idea. You're taking this equation, okay, it's a circular pool that you're filling up, right? And then you're trying to say, okay, with respect to time, you know what dA over dt is. You know this idea. This is known to you. And so to get this dt to pop out for all of these, because everything else is working with respect to time, you take d over dt of like everything, like both sides. And that will implicitly give you your final formula that you want to work with, which is then dA over dt, or t 2 pi r dr dt, right? Because 2 and pi are constants, which is another thing. Like, they will try and trick you. Like, they'll give you like derivative of e to the 32nd power. Like, that is a constant. Don't stress out trying to differentiate this. Anyway, so this is, a very typical related rates problem. Given this one, then you just solve for this using very simple algebra, and you just plug in the radius. So this is another thing, like the point of this radius, this r variable being here, is it's going to be like, at radius equals 1, this dr over dt is going to be some value. But at r equals 2, it'll be another value. And r equals 3 will be another value. And this one's going to be remaining constant. And that's why you're able to solve it in such an easy way. Because this one's constant. These numbers are constant. As soon as you know this, and because it'll be given to you, the question of this in the book is, at what rate is the radius expanding when the radius is 4 inches? Well, this is officially 4, so there's only one thing left. And what do we know about an equation with one unknown? You can solve it very easily, right? This is how you solve this one. And so, yeah, always try and work towards first building the equation that you need, or re-deriving it, re-remembering it. What's the volume of this? What's the volume of a cone? What's the area of a circle, area of a square? These kinds of things. Pythagorean theorem comes up. You're trying to relate maybe x-word motion, ladders are slipping and falling. Don't forget the dy over dt here is negative, that kind of thing. But the dx over dt is positive. Right, because the x length here is getting bigger and the y length here is getting smaller. Anyway, so when you set these up, you're saying, okay, x squared plus y squared equals some constant, which is the length of the ladder. Differentiate with respect to t. You're trying to get these dt's to pop out. That's what I keep saying. Implicit differentiation will let you get these dt's to pop out, or whatever differential you need. Just take the derivative with respect to that variable, and that it'll give it to you. You don't need to worry about anything else. So this one would end up being something like this. If you take the d over dt of both sides, dy over dt equals 0. And always remember this constant is going to be differential. This constant, the ladder's length, which is what this is, right? Well, the squared, you know what I mean? But anyway, the square length of this ladder is not changing with respect to time. That would be alarming. You know what I mean? Like, that would be not good. It's constant, so don't worry. It's a constant when you differentiate with respect to time. And this is that. As soon as you do that, well, this is a very easy problem. You're given some x. Maybe it's asking when the x length, when the ladder is like 5 feet away, when the base of the ladder is 5 feet away from the wall, where then you know that you can plug in the 5, but because of this equation right here as well, you can plug in the 5 here. You know the constant value of this, you can solve for the y, right? That's something that happens very easily. And then so now you know what the y value is, you know what the dx value is, maybe you don't, but you'll be given one of these differentials. That is given. Like, you won't, if you were given none of these differentials, you wouldn't be able to solve this, as far as what we know, right? So that's how that one will go. Just plug in what you have. That's, again, same idea. Construct an equation that makes sense. Differentiate in a way that'll give you the differentials you need. This one is very important to know. The cone, the conical tank, right? It'll be filled up at a rate, and the volume will be changing. And know that the radius is half of the height. The height and the radius is then half the height. This is a relation that you'll get with like a right circular cone. That's what it's called, right circular cone. That is a very important property, because when you see the volume of a cone, this is why you'll have several variables, pi squared, sorry. Pi squared h, right? This is important. Yeah, I remember why. Yeah, the cone, the cylinder, 1/3 of it is the cone's volume, as long as the radius and height are the same. So this is why it looks like a cylinder, and you'll derive these formulas in Cal 2. And so what the problem is here is if you want to maybe take a related rate with respect to t, both sides, I'm sure, great, that's something you can do. But the problem is you'll have two variables. You'll have r and h, and you don't want r and h because this is now too many variables, not a Cal 1 problem. Cal 1, you have a single variable calculus. That's what it is. That's why it's called that, right? And so you want to get your h with respect to the r, which is very easy. You just use this conversion. H, or maybe you get your r with respect to the h. You know, depends on the question is honestly too, because I might be asking for you to give the dh over dt, or I might ask to give the dr over dt value. So you convert one of these to look like the other, and then you're done. Basically, not really. You just differentiate and then plug in. Okay, positive acceleration and velocity. This is very important. Position is s of t. Velocity is the first derivative of position. Velocity is v of t. Acceleration is a of t. So if you were to relate it to some f of x that happens to be continuous everywhere and infinitely differentiable. Wow, I sound like a textbook, boring, right? So this happens, right? First derivative, second derivative, all that nonsense. Also, you know, things to note. When the velocity is positive, you're moving to the right because number lines get larger to the right, right? That kind of idea. And you're in 1D motion. Currently in Cal 3, you'll get to these same problems, but in 3D motion, they're actually very simple. But when you're in Cal 1, you're moving, it's literally talking about a particle. It's moving left and right in a single dimension. It cannot move up and down, horizontal, none of that. Sorry, horizontal, yes, but like, sorry, diagonal. It cannot move like that, right? But left and right is the only way it can move, even though you're going to be, you know, maybe graphically looking at its velocity, something like this. This is simply describing the velocity of this over time, but the output itself is just velocity, right? The output of this, if this is the velocity graph, but maybe it's the position graph. And if it's the position graph, it's not saying that the particle is moving up and down through the coordinate system until you're in a Cal 3 problem where you have to parameterize and it's respect to t and all these kinds of things, which you'll know. I think it'll be obvious to you. They'll be told, I think. But this, it's simply saying, okay, you know, at this time it's positive, you know, 3 positions. So maybe it's over here, you know, but maybe over here it's like -4. So maybe it's all the way over here. You know, maybe it's traveled all the way over here to -4. And that's the kind of what I mean by the same one-dimensional movement in this Cal 1 topic is being represented in a 2-dimensional graph. But absolute value, one other thing to remember, when velocity and acceleration have the same signs, the particle's speed is increasing. What is speed? Speed is the velocity, the absolute value of velocity. The absolute value of velocity equals speed in 1D. This is restricted to 1D, meaning you could be moving to the right, or you could be moving to the left, right? And the speed of you moving left or right, just taking the absolute value, not looking at the sign, looking at the magnitude, if it's a vector, the magnitude of the velocity vector will be giving you the speed. And this is that same idea will translate into higher dimensions if you just say magnitude, but absolute value works for 1D, right? You're just like, oh, if it's 3 meters per second positive, 3 meters per second for the velocity, or negative 3 meters per second, it's moving at the same speed, just in a different direction, right? Very simple way to look at that. And so if you look at the velocity graph, maybe it's doing something like this. The absolute value of that graph will just flip all of the negative sections of it over. And then this way, it becomes very obvious why if your velocity is positive and your acceleration is positive, you know it's speeding up. Because if this is the speed graph, if this is the speed graph, right, then you're saying, okay, you're speeding up because because you're going up and getting larger in the speed graph, right? That's the y value is getting larger. And what does that mean for the velocity graph? Well, you're getting more negative, which means your acceleration is negative, right? The acceleration is a negative value because the slope of the velocity graph, v of t, purple graph, that is negative, and you're in the negative quadrants, right? And so that's why both the signs agree. You're getting your speed's increasing. Another way to look at it is, okay, what's happening here? Your speed is decreasing. Why is it happening? Well, your signs are not agreeing. You're on the negative quadrants of the velocity, but you're getting less negative. You're getting less negative and more positive, and that's why the speed is decreasing here. And you can see it with the flip. And you can think of it like directionality. No, you just really kind of conceptualize it this way, and think, okay, if you're in the negatives, you're getting more negative, meaning you're speeding up in that same direction that you have been moving in. But if you're in the positives, you're getting more positive. So you are, again, getting larger in the direction you have been moving, right? So the magnitude of your velocities are getting bigger in either direction, right? Your -3 is going to -15. Speed is getting larger, obviously. And then your 3 is going to 15. Speed is getting larger, obviously. Okay. Okay. So, and if your velocity is 0, particle has stopped moving, right? So that is another thing to keep note of. And if it stopped moving, the velocity is neither, if it's 0, it's neither positive nor negative. This is a big idea. It's characteristics and numbers, right? If it's 0, it's not positive or negative. Well, it's not moving left or right. It's stopped moving. Some more derivative definitions come into hand. We have 10 more pages in this book, which are we've gone through like 180 so far. So derivative natural log of x, right? D over dx of this, 1 over x, right? D over dx of e to the x equals e to the x. This is the iconic one, right? But let's generalize this. So this is log of e. This is log e, log base e of x is natural log. And so if it wasn't log base e, maybe if it was log base b, what would you have done instead? Yes, like what is the definition? This is another derivative definition you should remember. For log base a of x, you think, okay, 1 over natural log of a times x, right? I think so. Let's look. Yeah. Well, and it's easier to see the x written before it because it's not confused with the natural log of ax. Anyway, so x times natural log of a. Well, if this a were an e, which is what I had before up here, if this were log base e of x instead, it would be natural log of e. What is natural log of e? It's 1, so it would just be 1 over x times natural log of e, which is actually, natural log of e, which is 1, which is why you see that derivative of natural log of x is 1 over x, because if you generalize it to any base, it would give you 1 over x natural log of a for the derivative. And if you have an a that's just e, well, then we'll just cancel with the natural log part. And the same kind of idea appears with the derivative of a to the x. Right? Okay. What about, I don't know why I just drew that. D over dx of a to the x equals, and I'll tell you just your face, is a to the x natural log of a. Right, and why does this make sense? Well, if this were e, it would just be, if this were just e, and we that specific case, derivative of e to the x is simply e to the x times natural log of e. Well, why do we, the e's replace the a's? What do we see again? Oh, it's 1. So that's how I remember those formulas. 1 over x, you just have the natural log of a at the bottom because it's a constant. A is a constant in that case, and natural log of a would be a constant. And here, again, in this case, a to the x, natural log of a. Same kind of idea. It is just another natural log of a. That's how I generalize and remember those very niche formulas. Okay. And I'm going to give you some final form. Honestly, I will show you some final formulas. Right. You'll see derivatives of inverse trig. These, right? For these, right, arc sine, it's just square root of 1 minus x squared. Arc cosine, -1, blah, blah, blah. Arc tan, that. Arc cotan, negative of that. And so when you add the co in front of the statement, cosine, cotan, cosecant, it's the negative of what you see for the sine, tan, secant, right? This is just the negative version of this, negative version of this, and negative version of that. Okay, so I guess pause it there and you can look at them longer. And then you think, okay, last idea. I want to go over inverse derivatives. And these get trippy. I was kind of reviewing these and I got a little frustrated because I was forgetting the whole idea. So if you're asked to take the derivative of an inverse function, right? Say y, come on, y equals f of x is some injective thing. It's an injective function. It's 1-to-1. Well, then this exists, and you can, prove it using Cal 1 ideas, like just take the derivative. And if it's always increasing, you know that it'll never come back to that same y value again, unless you have that same x value again, right? So, if this exists, right? I like to think, okay, it's no longer the y. The inverse of the y equals the x. And so, if you're now taking a derivative of this, right? This is the idea, right? Instead of having to do this entire process of taking f of x and making the inverse function using those swap the y and x tricks, if you want to find this, well, all you have to do is use the simple formula. And I'm going to plug in some value here. So let's say a is here. And it's simply 1 over f prime of f inverse of a. So this same input, whatever you're inputting here, is going to show up. I don't want to say that because it doesn't exactly show up that way. But the a that you input here shows up here, and all you're doing to find this value is derivative of the inverse of a. Derivative of the inverse of a, right? And I think of this 1 over thing as like a conversion method. Anyway, so what'll be confusing is they'll say, okay, find this inverse at x equals 3, right? It'll be so, discretely confusing, right? X equals 3, and you'll think, oh, it's f of, x on the f of x graph. No, the way I just stated it, find the derivative inverse at x equals 3, and then they'll give you a function, f of x equals maybe x squared, right? X equals 3 is referring to this, the inverse function, right? So x equals 3 would then, in this case, be 3. Sorry, the a would be a 3, sorry. And the a over here would then be a 3 as well. And so then you're saying, okay, what, and maybe it's saying where for x is greater than 0, so you don't have to worry about not being injective or anything. So you'll say, okay, what is the inverse of x? what is the inverse, sorry, of f of x, such that if you put in a 3, it'll output what we want. And so honestly, you can kind of look at this. 3 is equal to x squared, and x is square root of 3. So that's what this input would be. So then it would be f prime of square root of 3, 1 over f prime of square root of 3. And then you would have to know that f prime in this case is just 2x because of differentiation. And this was a very bad way of showing it. What I want to show, and I just quickly wanted to go over the way you might commonly see it with x equals 3. And you'll have to understand this is with the inverse, and you'll just plug in this formula, right? But sometimes they might say y, like as in like the letter y. They might say, okay, you have something that looks like this. Give me a second. You might see this. Oops, sorry. You might see f of x equals x squared plus 4 or something. And you say, okay, and they say, okay, find the derivative of the inverse of this function when y is equal to 29. And they're not referring to the y of the inverse. They're saying when y of this is 29. And this is when it gets really confusing, because the y of the inverse function is the x of the input function. And it's all this kind of crazy stuff, right? And so, and what we want is actually the x of the input function. So if you can catch that, this would actually be 29, because we want the x of the input function. But before we get there, right, this is how I always set it up on my paper. I say, okay, I say f of something, equals this, and f of this, same this, will give us something, right? And the way why I line it up this way is this y value can just be simply the same as this one. So you say, okay, you write this down immediately, right? You don't know what you've been given, and then you read the problem, and they're like, okay, the y is 29. The y of what? The y of the f of x function is 29. So I think, okay, the y of the f of x function is 29, which then drops down here. That means the 29 is the input of the inverse function, and this is just a very nice way to package this whole idea. You just standardized it, boom. So no matter what they say, you'll be okay, right? I guess that's a good slogan. But if I go back to that example that I quickly and hastily gave you, if they had said x equals 3 and they were referring to the input function, and you were able to deduce that based the way they kind of, I guess, word it and kind of need to assume sometimes for inverse functions. If they said x equals 3, well, okay, the input of this is x equals 3, because this is the inverse function, and that means the thing above it is also 3. And that means, and then, of course, to use this function now, use this formula, you would have to do that whole thing where, okay, well, I know what I want to plug in here is 3, and that means this is 3, and why do I support that claim? Because, of course, the inverse. This is inverse, sorry. If that was confusing at all, that's not a derivative, this is an inverse function. If you input the 3, you'll get it'll produce some output, which if you put into the original function, it'll produce the 3. And this idea is supported here. This is the same inverse function input, same inverse function input, right? That's the idea I want to get across there. But if they were said, okay, no, it's, they say y equals 29, right? They say y equals 29. Well, then okay, 29 goes here, 29 goes here. Oh, I just filled in the inverse function's input. That's exactly what I wanted for my formula, right? That's exactly what I needed, because then I can do this, right? And then you'll need, and then for, of course, f inverse of 29, well, you only need to know what that is for one step. Well, what do we think? What can you deduce that f inverse of 29 is? Of course, positive or negative 5. Let's just say x's are greater than 5 for this case. Well, then this would be positive 5. Well, then, okay, how do we use this equation? F inverse of 29 is positive 5. It's positive, question mark is equal to positive 5. So f of 5 equals 29. This whole circular idea, 1 over f prime of 5. Okay, then what is f prime of x? It's a very simple power rule problem. 2x equals f prime of x. And so evaluate that at x equals 5. Sorry, if you evaluate that at x equals 5, this is 10, right? Equals 10. Boom, this is 10. So the answer is 1/10, right? So all of that confusion about which input is what and all that kind of stuff, I hope is simplified by this little thing here. I'll actually just write it again.